Turns out that the biggest joke in physics is simple harmonic motion. This stuff can be anything but simple. I don't even know if this is going to fit on an entire page. I'm going to have to try to make this really, really small or something. So let's start by taking a look at simple harmonic motion. And I'll draw a little graph. What it only means is something going up and down like this, oscillating, right? So let's just draw a graph real quick and simple here. Let's start with our maximum displacement. We'll draw the origin right here. We've got our maximum displacement up here. This is our xm, maximum displacement. And then that's just going to do this type of thing. And then we're going to end our period right here. So it's essentially a cosine, right? Great. That means that we can say that x max is going to be, let's say, x of t equals xm cosine, and it's going to be wt plus this phi thing. That's going to be the phase constant, and this whole thing is the phase. So when it's plus on the phase constant, this is actually going to be shifted to the left. So plus phi, and then if it's shifted to the right, that would be negative phi. Great. So now we kind of see how the phase constant works. This is a cosine function, and that's the maximum amplitude. We can also sometimes represent that as capital A. Sweet. So that's going to be that. Now, of course, if we have a displacement, we're also going to need velocity. So we can write Vmax, Vt, is going to be equal to, let's take the derivative of the displacement to find velocity, right? That's just going to be negative xm w. Okay, and I'll put this in brackets actually. Brackets, because Vmax equals this component when, we'll go ahead and do the sine Wt plus phi. Okay, Vmax is going to equal that when t is 0, I suppose. Kind of weird how this works, but it's basically how it works. So we're going to go Amax. This is for the derivative of velocity. We're going to go to Amax. A of t equals, and this is negative xmw squared. Cosine again, wt plus phi. These are going to be the three equations that we can derive from this graph. Displacement right here. Displacement. Good vocabulary word. And then we've got the velocity, which we could set equal to xmw. And we've got the Amax, which we could set equal to xmw squared. Again, when t equals 0, that's going to be accurate. And so from A equals the acceleration equals xmw squared, right? We're going to need some sort of a force. You can kind of think of this like a magnet. Here's this thing right here. This is sort of the average point. And if something goes further away from the average, xm up here, the maximum movement away from this average line, it's going to sort of want to be pulled back like a magnet towards this average line. When it comes back down here, it's going to be negative xm. It's the maximum negative, and then it's going to want to be sucked back like a magnet towards this. You're going to need something called a restoring force. Restoring force, and that's going to be F equals ma. But what's A? A is going to be xmw squared. All right, and this may or may not be negative. It's probably a negative. We'll put that negative right there. All right, and that's essentially right, because when you are moving further away from this positive direction, you need a negative restoring force to pull you back down, kind of like the negative force of gravity, I guess. But anyway, let's just go ahead and keep going. Now we want to specify some variables here. Let's specify t. I'm trying to find where I can put this, make enough space here. I'm going to define t up here. T is just going to be equal to period. That's the period. It's going to be 2 pi over w. We know about this already. That's the speed that it takes something to go around the entire w. That's the speed is going to be in the entire circumference of the circle, 2 pi, and the time it takes. It's a period. T is also equal to 1 over f. All right. And in fact, I'll make that a separate equation. T equals 1 over f. So that way we can sort of figure out that, W is going to be equal to, let's say, 2 pi over T. That makes sense. And then we can also say that W equals 2 pi f from all that. All right. So these are just going to be some periods and some ways to get the angular velocity from this. Okay. Now, I think this is a good place for us to sort of start taking a look at some examples, and there's going to be sort of 3 examples of like how this actually starts working in the real world. So again, we got the graph, we got positive x displacement there. It's going to need a restoring force that'll suck it back towards the center. It's going to oscillate towards the other side and sort of reverse itself. We still need the positive force on that side because we've got a negative x. And then we've got this time period way to describe this and the angular velocity ways to sort of represent that as well. I think everything here is pretty clear so far. Now, before we move forward, it's probably helpful for us to take a look at small angle approximation from calculus, essentially. So if we got some small angles, then sine of theta at a very small angle is approximately equal to theta. We just have to start trusting these claims that I'm going to make. I'll make 6 claims that when angles are really, really small, this is basically what's going to happen. So when cosine of theta is really, really small, that would be essentially like 0, right? Well, then it's going to be equal to 1, right? 1 minus theta squared over 2, which should be approximately equal to 1. If we want to get exact, it'd be sort of this stuff right here. And then we've got tan theta is approximately equal to theta. So these are just some claims that I'm going to make. When things are really small angles, theta is really small, sine theta equals theta, tan theta equals theta. Just trust me. And then we've got xm is going to be equal to r theta. This is actually saying that the arc length s equals r theta, but I'm putting xm there because let's say if we were doing something like this, and this was your arc length right here, see that you usually call that s, but because that's the maximum displacement right there, I'm going to replace the letter s with the letter xm because they're essentially saying it's the same thing here. So I might redraw that in just a second. And then we've got Vm equals Rw and theta max. And notice how I didn't put theta max here. Sometimes you might see this as theta max. Sometimes you might see it as theta by itself. Sometimes you might even see it with in the parentheses t, like this, theta parentheses t. So there's like a lot of different ways that you can sort of write out these equations. W squared theta, and that's going to be like this. So I wrote it in 3 different ways: theta by itself, theta max, and then theta with the parentheses t here, because sometimes they refer to these things in different ways. So we're just going to write it like this, and hope that this sort of generalized version. There's so many different ways to write these equations. I'm trying to be as general as possible and sort of show different examples of this. So this is small angles. When the angles are about less than 20 degrees or so, then this stuff would hold true. This is for small angles. The first example of simple harmonic motion and restoring force that we're going to use is a pendulum. So I'm going to draw the pendulum here, just like this. And we can see how if it were right here in the middle, that would be essentially the equilibrium point, our origin. When this is pushed this direction here, this is xm. And when it's over here, this is obviously negative xm. And there are many different things that we can say about this. First of all, when this is at its maximum height over there, we can say that there's a specific h right here. We're going to have the force of gravity that's pulling against that, right? So the restoring force in this particular case, in a pendulum, this is a pendulum, is going to be gravity. That's going to be the restoring force that's going to be pulling this thing forwards and backwards, all right? I'll try to write that like this. F equals mg, and then we got x over L. Now, it's a little strange how we got to this. We had to do some small angle approximation. I had to set, I had to do a bunch of different calculations here to figure this out. But, we're not going to go too far into that. We might go into some more examples in other situations, but for the simple pendulum, just believe that the force of gravity here, this is the restoring force. When we figure out what this is and we plug that in there, you could use that, but that would actually equal this. Okay, and so that's going to be a restoring force. Now let's go ahead and take a look at the period, for example, T. And again, that's going to be the force of gravity that's pulling. I'll try to draw this here. Because let's say this H was the force of gravity, even though that's technically the height. It's not going to be, like, the restoring force is pointing this way. So we actually have to figure out what's the force of gravity in this direction. Not pointing straight down, but in that direction. So it's going to be a really small force. All right, just to make it very clear that this is really what that force is. That's F. Is the force that's this direction. It's not going straight down. It's the force that's that direction. That's why it's kind of not mg. It's mg with this weird little angle here, and then there's a sine of theta in there, and then, well, sine of theta is actually small degrees, and so now we've got x over L. And L is obviously the length here. Now, sometimes you might see that as L, sometimes you might see that as R, the radius, so just be very careful here that you don't get too confused. L, R, radius, same thing, and then the X is obviously XM right here. Okay, good. So I think we figured out what the force of gravity in that direction is, okay? And it may be negative as well. I'm not too worried about the negatives at this point. But we've got some variables that we have to explain, and there's also two types of pendulums, so let's not be too hasty here. There's going to be the pendulums that are basically really complicated with they have a weight that's maybe like here or here, and they got some strange weights in different locations and stuff. You might have to add up the inertia and figure out what the inertia is of this pendulum. So if you're going to do that, then the period would be 2 pi square root of I divided by mg x com. That's x center of mass right there. That's going to be the period for a pendulum. It's really complicated. You got to figure out where the center of mass is, and then that's going to be your center of mass, not xm, that's x center of mass. So it could be here. This might be the center of mass. I won't even put the x there, just to be not even confusing. That might be the center of mass of this particular pendulum. So that's going to be what you put in for that in terms of the radius. That's the center of mass there. And square root of I, you got to figure out the inertia, etc. So yeah, this is kind of complicated. But anyway, let's go into the W. And we got W is going to be square root of LMG divided by I. Okay, so that's going to be the angular velocity and the period of a pendulum that's really complicated. You got to do a bunch of different, figure out what I is, the inertia and stuff like that. But let's say we had a simple pendulum and it was just basic and you just had the weight right there and I was just simple and it was just mg. Well, in that case, what you would get is T equals 2 pi, and then the square root of L over G. And that's going to be the simple pendulum. Simple pendulum right there. And of course, with the W is going to be equal to square root of G over L. All right. And this just comes from, figuring out these T's from before, putting that on in there. So I think that is relatively good for the variables of the pendulum. But now let's take a look at how we might be able to solve this stuff with kinetic energy and potential energy. Well, finding the potential energy of a pendulum is actually really easy. You just have to find the center of mass, and then whatever that is, use the height to just calculate the potential energy. So I think you might remember height was supposed to be equal to R1 minus cosine theta. Remember this from the previous example. I don't know if that's even legible though. R minus 1 minus cosine theta. So if you use a height for whatever your your center of mass is, you're going to need to plug that into the U, which is mgh, and that's going to be right here. When the potential energy is the maximum, it's going to be at the top right there. And then once it comes down to here, at that point, that's when we know that the kinetic energy is also equal to the same thing. I mean, it's equal to U max. So once it comes there, kinetic energy is equal to U max, and U would be 0. So essentially, both of these two things are supposed to add up together to be always equal to U max. U max, and that's going to equal K max and all that stuff. Yeah, so just making sure that it's always only equal to the energy at any point of this situation is only equal to the maximum potential energy. This should help you to solve any kind of pendulum energy problems, because it's pretty easy. You just use the potential energy and then just make sure that it's always just the total is equal to that. So if it's here, the kinetic energy is just equal to the maximum potential energy, and obviously the potential energy is zero. That's pretty easy. So let's take a look at the next restoring force, which is going to be the spring force. Spring. This one's not too bad. Okay, so we should remember that F equals negative Kx, and that's just equal to ma. So let's just say m d squared x over dt squared ma. We can also say that negative Kx equals ma, simply put. And let's put a little star around this one, because this is an important equation. This might help you solve some homework problems. And then from here, we should remember that a equals negative w squared x from over here, right? And so we also know that w is actually just equal to the k over m. This is just given for spring. Is something that we just have to know. Again, these variables, these t and these w's, are generally given to us. But when we square that and we put that in this, and we actually get something like this, where the d squared x over dt squared, that's going to be the a component here, is equal to simply k over mx. And this is another important equation that may help us solve some homework problems. So these two kind of cool things here. And then we'll just put the period is equal to 2 pi, and then here is m over k. So it's going to be the angular acceleration of the spring force and the period of the oscillations back and forth. And now, if we draw a little example here, here is going to be our spring. This is just pulled downward in this direction. We don't really have enough room to do the upward side, but essentially you're going to have it coming down, and then it's also going to go up and down and up. It's basically like that, but I'm doing it on the side, just so it's on its side. And then we're going to take a note from before that, well, technically it should be the spring force that is like pushing in this direction right here, like sideways kind of, but it's not really pointing exactly, it's not really pointing at like a, it's not really pointing at the right angle here. So you kind of have to do some calculations and some derivations, and eventually once you get to this 90-degree angle here, you will get, after some calculations, that this F, the restoring force, is equal to kr theta. That's an approximation. Okay, this is the small angle approximation that we did before. I'm not going to go too far into how this was derived, um, but essentially you want to do some calculations here, the sine and the angle, etc., etc. Put this at 90 degrees, and you'll find that F equals kr theta. That's going to be the restoring force of this. I guess I'll show you kind of quickly how I got there. Because here's your theta, and if you put this line here, you make that perpendicular, you're going to get two similar triangles. Here's theta again right here. Theta, and then you can take the sine of theta. Well, you just kind of have to trust me a little bit on this one. I don't really have too much space to go into that. So this is the spring force that we have here, and we got the F equals kr theta, similar to what we had over here. F equals mg, that, and then over here, this one. So these are just the restoring forces, 1, 2, 3. And let me just draw one more little thing here, because it turns out that if something is a little spring, has been got a little weight on it right here, you can actually experimentally calculate by seeing what was the change of the equilibrium. Obviously, the equilibrium should have been like here, right, from before, but it's been pushed down because of the weight. So you figure out like what distance that was pushed, and you can set that equal to mg over k, and that'll help you to figure out what k is. If you need to experimentally figure out what k is, turns out that k should be equal to mw squared if we go out through all this. So that's just kind of like the basic equations for the spring force. We can take a look at how to solve this stuff in terms of kinetic energy and stuff too. Well, to calculate the kinetic energy of the spring moving back and forth, we just set kinetic energy is 1/2 mv squared. We know that the v squared situation is just this, xw sine, stuff like that from this. We could square that. Let's set kinetic energy is 1/2 m, and then we've got x squared, and then w squared, and then we would have the sine squared. We'll deal with that later. Let's ask ourselves what w squared is, and from before, w squared is actually just k over m. If we start plugging this into the equation now, we would get ke equals 1/2 m, and then xm squared, and then k over m. We can actually cancel out the m's, and we'll be left with ke is equal to 1/2 k xm squared. And turns out that that is going to be the kinetic energy. Well, let's not forget the sign. But I'll write that down here actually. So kinetic energy equals 1/2 k xm squared, and then we've got sine squared wt plus phi, and then we would also have the potential energy at that point, because once the kinetic energy just like before, it was going to be like this. So the kinetic energy at maximum is going to be right here at that 0 point. Once it goes up here, this is going to be the maximum potential energy. We can put that right here. It's just going to be the negative of this, or not the negative, but rather the cosine version. So 1/2 k xm squared cosine squared wt plus phi. That's kind of an interesting result there. And then we have the total energy at any point is actually just going to be equal to 1/2 k xm squared, because these two, when they're combined together, it would just be equal to 1. And so this is going to be the total kinetic energy right here. So that's pretty cool. Awesome. Simple. The kinetic energy of the spring is simple. The spring is relatively simple. It's moving back and forth. Simple harmonic motion. We're actually getting somewhere here. Let's take a look at the next example. All right, this is where things get interesting. The third restoring force. It's actually going to be restoring torque. So now we actually have torque, which is equal to negative kappa theta. Before it was restoring forces, now it's restoring torque. It's going to look exactly like this in the sense that it's going to be twisted wire. All right, this is a twisted wire. Twisted wire. The wire would have to be right here, and we twist the wire a certain distance, and then we let go, and then we see what happens. All right, it's very similar to the spring, but it's actually, the spring would be here, attached there, but the wire, the twisted wire, would be just right here, and there would be no spring there. There would just be the twisted wire along a stick, and then you just got the stick by itself. But still, that little torque right there is, there's going to be this kappa theta involved. I'll go ahead and write all these different little ways to rewrite torque. IW squared theta. We'll figure out how we came to that. RF, IA. This is all different ways to rewrite the restoring torque. Okay, and let's start with some more derivations over here. We'll go IA is equal to negative kappa theta. Okay, and then we've got, let's try to replace alpha with d squared theta over dt squared, second derivative of theta. Put that negative k theta. At this point, we can do this. D squared theta over dt squared equals negative kappa over I. That's inertia. These are all kappas. And then theta. Now, let's see what W is equal to in this particular situation. Kappa over I. All right. This is something that's, I guess, sort of given to us. They even give us the time, the period. So I guess I'll just write the period on top first. So period is going to be equal to 2 pi I over kappa. And that means that W is equal to the square root of kappa over I. And from that, we can actually determine that kappa is just equal to IW squared. Bam! And so we can divide I on both sides, and we'll get that W squared is K over I. Now we can plug that in here. So this is just negative W squared theta. And this is alpha, right? So now we get that alpha is negative W squared theta. Whew. All right. And that is how now we can start getting the final little kinematic equations over here, because we started with alpha, and then now we're going to sort of take the double integral of that. We'll get theta. So theta t is equal to theta m sine wt plus phi. And then we've got wt, that's going to be equal to w theta m cosine wt plus phi. And then what we have originally right here, alpha, that's negative w squared theta sine wt plus phi. Bam. Now, yes, these are going to be the kinematic, angular kinematic, I guess. Angular kinematic for simple harmonic motion. So it's not even kinematics, it's just the angular simple harmonic motions equations kind of over here. One last thing before we move on to the kinetic energy is we just need to take a look at the torsion constant. Torsion constant. That's kappa. And we'll just relate that to the spring constant with the r squared. Kappa is the spring constant times r squared. All right, now let's take a look at this energy that we have over here. It's just going to be rotational kinetic energy at this point, which is 1/2 I W squared. And if we square W right here, then we'll get 1/2 I, and then we've got W squared, theta squared, cosine squared, WT plus phi. And as you know, when it comes to this stuff, we can actually just set the potential energy equal to essentially the sine version of this. So 1/2 I W squared theta squared sine squared WT plus theta. And then you can also set the total energy equal to this cosine and the sine will essentially cancel out, and you'll get the total energy is going to be 1/2 I W squared theta squared. Awesome. So now we've finally broken this apart into our three separate components of simple harmonic motion, which I think are actually not too bad. We essentially just have the restoring force and the energy, and maybe just the force and the energy that we kind of have to deal with. And this time it's going to be just following this graph, using these kinematic equations here, or simple harmonic equations there. And then we've got the pendulum in this situation, a little bit more complicated one in the simple version. And we've got the spring type of forces going back and forth, and the torque, again, from just a twisted wire. It's going to look exactly the same as that one. Here's the energy version for that. Well, anyway, this stuff was all relatively complicated, but I think gravity in the next section is going to be much easier. We can take a break on that one. So if you enjoyed this kind of stuff, make sure to like and subscribe and just ask some questions in the comments. Oh my god, this stuff was nuts.